So in this session we will have a look at another memory interfacing example. Here again we are going to try to interface some memory chips to the 8088 processor. Again, 8088 processor has a 8-bit data bus. So we will be looking at initially examples using 8088. So what we are going to try to do here is we are going to try to connect memory chips or certain memory chips to 8088. Now in this particular system we require 4K of ROM and 8K of RAM. So 4K of ROM, the chips that are going to be available are going to be 2716 and the RAM chips available are going to be 6116. Now one more thing that is given here is ROM has to be connected from address 000, whereas the RAM interfacing is going to be from address 0800. So it is not necessary that these are continuous. ROM is going to be starting from 000. You require 4K of ROM and you're going to require 8K of RAM, which are going to be connected from address 0800. So these are not continuous addresses. There is going to be a break in the address. So 4K of ROM and 6K of RAM, and the chips which are available are 2716 and 6116. Generally the ROM chips start with the prefix 27 and the rest of the numbers are going to give the size of the ROM chip. So for instance, if the ROM chip is 2716, the last two digits here, 27 says it's a ROM chips. The rest of the numbers, which is going to be 16, you have to take it and divide it by 8. So 16 divided by 8 would mean that the size of each ROM chip is going to be 2K. Similarly, RAM chips always start with a prefix which is going to be, in this case, 61. So 6116 again, 61 indicating it's a RAM chip. The rest of the digits are going to indicate the size of this RAM chip. So you take the rest of the digits, which is going to be 16, divided by 8. The size here again, the RAM chips are going to be 2K RAM chips. Now if I say that the ROM chip available is going to be 27256, in this case 27 is going to indicate that it is going to be a ROM chip. The rest of the digits 256 are going to give the size. So the size of the ROM chip is going to be 256 divided by 8. So it means it is going to be a 8K ROM chip. So you can take the rest of the digits and you can find out what is going to be the size of the chip. So what we have to do, we have to have 4K of ROM in the system. You need to have 8K of ROM, but the chips that are available here are going to be 2K ROM chips, and again these are going to be 2K RAM chips. So you cannot use one chip, you would have to use a series of chips in order to get 4K of ROM and 8K of RAM. So how do we go about connecting them? The first thing you have to do is you have to look at the number of chips or the memory requirement. You are going to have 2716, which is going to be ROM. This is a 2K chip. We need totally 4K of ROM in the system. So the number of 2716s or the number of ROM chips required would be 2. Now similarly we have RAM chip which is 6116, which is a 2K chip. We require 8K of RAM in the system. So to get 8K from 2K chips, you are going to require 4 of these RAM chips. So you are going to require 2 ROM chips and you are going to require 4 RAM chips. So totally there are 6 memory chips which are going to be available in the system. 2 of them being ROM and 4 of them being the RAM chips. So now that we have decided what is going to be the number of ROM chips and the number of RAM chips, we also have to see how the memory mapping is going to be done. Remember, the question says that ROM is going to start from address 000 and RAM is going to start from address 0800. So we have to see how to connect these addresses, which are going to be 000 and 0800. So first let's do the ROM interfacing. We have 2 ROM chips, ROM 1 and ROM 2. So each of them are going to be 2K chips. So you have to allocate 2K addresses to them. So ROM is going to start from address 000. The first 2K addresses would be from 000 to 007FF. That is going to be the 2K addresses which are given to ROM 1. We require 4K, so we said we are using 2 ROMs. So if the first ROM is going to finish at address 7FF, the next ROM would start from address which is going to be 00800. So ROM 2 is going to be from address 00800 to 0FFF. This is going to be the total 4K ROM which is going to be in the system. ROM 1 and ROM 2. We are using two 2K chips, and this 4K ROM, as the question says, starts from address which is going to be all zeros. Now we have to connect the RAM chip. So totally we are going to have 8K of RAM in the system, and the starting address is 08 followed by 3 zeros. So we are going to have 8K, and again remember we have 2K chips. To get 8K, we require 4 such chips. The first chip, of course, must start from the address that has been given, which is 0800. So you give the first 2K block. So 2K means if you start at address 0800, the last address would be 087FF. So if the first RAM finishes at 087FF, the next RAM must start at address which is going to be 08800. And goes up to the 2K addresses which is 08FFF. So if RAM 2 finishes at 08FFF, the next RAM will start at address which is going to be 0900, goes up to 097FF. The last RAM chip will start at address 09800, goes up to address 09FFF. So these are going to be the total 4 RAM chips which are going to form 8K of memory, starting from address 0800. The last address would be 09FF. Each RAM chip is given 2K of memory. So we have 2 ROM chips and we have 4 RAM chips. So we have decided on the number of chips, we have decided on the memory map. The next step is we have to do the decoding. So in order to do the decoding, we have to look at the addresses in a little more detail. We have to look at it in the binary format. Of course, one thing we can see already is A16 to A19 are all going to be zeros. So let's avoid expanding it. We'll only expand A0 to A15. So A0 to A15 of the first ROM chip, which is going to be from 000 to 07FF. You have the address lines A0 to A10, which are going to be used for selecting one of the memory locations. And then we have A11 to A15. For ROM 1, it is going to be all zeros. For ROM 2, since it's starting from address 0800, it is going to be 000 and A11 is going to be 1. RAM is going to start from address 0800. And it is going to go up to address 087FF. So this is going to be again the binary format of the first address and the last address. So similarly, we can get the binary format of the rest of the RAM chips, RAM 2, RAM 3, RAM 4. Of course, A0 to A10 goes directly to the memory chips. Now we have to use A11 to A15 for decoding. You have to decide which of the address lines from A11 to A15 you are going to use. So if you look at the memory mapping, again what you will notice is in the binary format, A13 and A14 are going to be 0 for ROM 1, they are 0 for ROM 2, they are 0 for RAM 1, they are also going to be 0 for RAM 2, RAM 3 and RAM 4. So we cannot definitely use A13 and A14. So that leaves us with address lines A11, A12 and A15. So if you look at these address lines, A11, A12 and A15 are all going to be zeros for ROM 1. So for ROM 1, A15 is 0, A12 is 0 and A11 is also going to be 0. In case of ROM 2, it is going to be 001. You can see in case of RAM 1, it is going to be 100, right? So 100 again you have to remember is going to be equivalent to 4. So ROM 1 was 000, ROM 2 was 011, RAM 1 was 100. Now if you look at the other RAM chips, for RAM chip 2, it is going to be 101. For RAM chip 3, you can see it is going to be 110, and for RAM chip 4, it is going to be 111. So we are going to make use of A15, A11 and A12. So this is going to go to the decoder. So the decoder is going to get A11, A12 and A15. A15 connected to A, A11, A12 connected to B and C. Now what we are going to do is, if it is going to be 000, ROM 1 should be selected. 001, ROM 2 is going to be selected. If it is going to be 100, in that case it was RAM 1. 101, it was RAM 2. 110, RAM 3. 111, it was RAM 4. So output 4 to output 7 is connected from RAM 1 to RAM 4. Output 0 and output 1 are connected to ROM 1 and ROM 2, which leaves output 2 and 3 unused because we didn't have any memory map in that area. So this is going to remain unused. Coming to the enable, again, if we are going to go back and we are going to look at the memory map, what we can see is that A13 and A14 were consistently low irrespective of the ROM or the RAM chip. So A13 and A14 are going to be the enable lines, and we also said A16 to A19 are always going to be low. So when they are always low, the output of the NOR gate is going to be 1. So G1 is going to be activated. So since again here I have made use of all the address lines, this is going to be absolute addressing. So we have made use of A11, A12, A15 to select between the different memory chips. So what we did was, we decided on the number of ROM chips, number of RAM chips. We did the memory mapping. We expanded the memory mapping and got our decoding logic. Now if you're going to look at the entire memory interfacing circuit, it doesn't stop here. We only did our decoding logic, which was going to be up to this point. So if you're going to look at the others chips which are going to be there, we have to connect ROM 1, ROM 2. We also have to connect RAM 1, RAM 2, RAM 3 and RAM 4. So we also have to connect RAM 1, RAM 2, RAM 3 and RAM 4. And we are going to be making use of the entire memory map. So you have the read and the write signals which are connected to memory read and memory write. You have the address lines A0 to A10 which are used for selecting between the memory locations within the ROM chip and the RAM chip. Because remember, each of these chips are going to be 2K. So A0 to A10 goes as address inputs to the ROM and the RAM chip. And of course, the output of the decoding logic is going to go as chip select. You can also see that the data lines D0 to D7 are connected to D0 to D7 of the data bus. In case of ROM, you only have the read signal which acts as output enable. In case of RAM, you have read and write. ROM, remember, is read-only memory. So since it's going to be read-only memory, we are only going to have the memory read signal. And in case of RAM, you can read or write. So you have memory read as well as memory write. And the address lines A0 to A10, which are used for internally by the memory chip to select one of the memory locations. And the rest of the address lines we used for decoding. So this gives the complete memory interfacing circuit from the system bus side of the interface to the memory. So this would be the final memory interfacing circuit which you get for any interfacing design problem, which is going to be, you will be given an address. From the address and the memory chips which are given, you have to design the complete memory interfacing circuit. So this is going to be the complete memory interfacing circuit. So we'll stop with this in this session. We'll see more examples in the following sessions.